Have you ever noticed how AI sometimes forgets what you just told it? Maybe you mentioned you dislike coffee, but a few prompts later, it's recommending espresso again. This isn't just a minor annoyance. It highlights a fundamental challenge in artificial intelligence: memory and context. Unlike humans, AI agents often struggle to remember key facts or preferences across conversations. This gap has sparked a wave of research, all focused on making AI memory more persistent and human-like. In this video, we'll explore how databases have quietly become the backbone of AI memory, transforming how agents remember, reason, and interact. AI's forgetfulness isn't just a technical quirk, it's a real barrier to making conversations feel natural. When an AI loses track of your preferences or the flow of a discussion, it breaks the illusion of a thoughtful, attentive partner. This problem has driven researchers to ask, how can we give AI agents a memory that feels more like ours? How can we make sure they remember important details and use them when making decisions? The answer lies in rethinking how AI stores and retrieves information, and that's where databases come in. The earliest attempts at AI memory were surprisingly simple. Developers used what's called the prompt engineering approach. Here, the AI's memory is just the conversation history, fed back into each new prompt. Sometimes, models are fine-tuned with user data, or given long histories as examples. This method is easy to implement and works well for short, simple interactions. But as conversations grow, so do the prompts, making them expensive and unwieldy. Plus, there's no real structure or semantic understanding, so the AI can still lose track of what matters most. With prompt engineering, the AI keeps a running context by concatenating previous messages into each new prompt. Some systems use instruction tuning to teach the model specific memory behaviors, while others rely on in-context learning. This approach is fast and requires no extra infrastructure, making it ideal for small, one-off use cases. However, as the conversation grows, token costs explode, and the context window eventually cuts off, limiting long-term memory. There's also no way to organize information semantically, so important details can easily get lost. As AI evolved, so did its memory systems. The next big leap was the vector database approach, inspired by retrieval-augmented generation, or RAG. Here, every piece of conversation or information is converted into a high-dimensional vector using embedding models. These vectors are stored in specialized databases like Pinecone or Weaviate. When the AI needs to remember something, it turns the current query into a vector and searches for the most similar stored memories. This method brings AI closer to having a searchable, semantic memory, able to find relevant information even if you phrase things differently. Vector databases revolutionized AI memory by enabling semantic search across vast amounts of unstructured data. Each conversation turn or document is embedded as a vector, and similarity search retrieves the most relevant memories. This approach is well integrated with modern AI stacks and scales efficiently. However, it's not perfect. Recall can be imprecise, sometimes returning irrelevant results. Managing these databases requires ongoing pruning to avoid bloat, and they struggle with structured relationships between entities. Another breakthrough came with graph databases and entity-based memory. Instead of storing flat vectors, these systems build knowledge graphs, networks where nodes represent entities like people or concepts, and edges represent relationships. For example, if you tell the AI, John is my teammate who prefers Python, it creates nodes for you, John, and Python, with relationship edges like teammate, of, and prefers. This structure allows the AI to reason about relationships and temporal sequences, making memory retrieval more human-like and context-aware. Several research projects have advanced graph-based memory. MemGPT treats large language models like operating systems, managing memory hierarchically. ZEP introduces temporal knowledge graphs, while Mem0 dynamically captures and organizes information from ongoing conversations. These systems excel at modeling relationships, handling complex entity interactions, and reasoning about when things happened. However, as the graph grows, so does its complexity, making maintenance and integration more challenging. As AI memory matured, researchers realized that no single approach fits all needs. Hybrid architectures emerged, combining multiple memory types. These systems use vector databases for semantic search, graph databases for structured relationships, key value stores for simple facts, and traditional databases for structured data. By leveraging the strengths of each, hybrid systems offer robust, comprehensive memory coverage, handling both structured and unstructured information with greater flexibility. Hybrid memory systems bring the best of all worlds. Each memory type is optimized for its use case, resulting in more robust and comprehensive coverage. These systems can handle both structured and unstructured data, delivering better performance across diverse tasks. However, this flexibility comes at a cost: increased complexity, higher infrastructure demands, and potential consistency issues between different memory stores. Maintaining and optimizing multiple components can be challenging, but the benefits often outweigh the drawbacks. Despite all the innovation, sometimes the best solution is the oldest one. Relational databases have powered applications for decades, from social media to banking. Now, they're being used to give AI agents structured, persistent memory. Instead of relying on exotic new systems, developers can use trusted SQL databases to store both short-term and long-term memories. This approach leverages mature, scalable technology that's already proven in enterprise environments. In traditional database approaches, memory is stored in structured tables with explicit schemas. Short-term memories, like recent conversations, live in one table, while long-term memories, such as important facts and preferences, are promoted to permanent storage. AI agents use SQL queries to retrieve relevant information, benefiting from decades of database optimization. This method is reliable, easy for developers to adopt, and integrates naturally with existing applications. One standout example is Memori, an open-source memory engine designed to give AI agents human-like memory on top of traditional databases. Memori combines short-term and long-term memory, letting the AI decide what's worth keeping. It models relationships and entities using structured records, rules, and intelligent tagging. This approach is database agnostic, supporting PostgreSQL, MySQL, and SQLite, and integrates with any LLM stack. The result is a reliable, production-ready memory system that feels continuous and human. Each memory approach has its strengths. Prompt engineering is great for simple, short-term needs. Vector databases excel at semantic search over large, unstructured datasets. Graph databases shine at modeling complex relationships and reasoning about entities. Hybrid systems provide comprehensive coverage, while traditional databases offer reliability and structure. The key is choosing the right tool for the job, or combining them for the best results. AI memory has come a long way, evolving from simple prompts to sophisticated hybrid systems. Today, databases old and new are at the heart of this transformation. With tools like Memori, Zep, and Letta, developers can finally give AI agents a memory that feels truly human. The journey isn't about reinventing storage, but about blending the reliability of proven systems with the intelligence of modern AI. As research continues, we're getting closer to making AI agents unforgettable companions, capable of remembering, reasoning, and interacting just like us.